Hi everybody, I'm David, and tonight we're going to be talking about chain replication, which I think is an interesting idea, and something that I don't see a lot in actual systems. So I think this is going to be fun. So just to kind of quote from the abstract for the paper to give you a sense of what it's all about. Chain replication is a new, as of 2004, approach to coordinated clusters of fail-stop storage servers. It's intended for supporting large-scale storage services with high throughput and availability without sacrificing strong consistency guarantees that are kind of nice, although that's something that people aren't doing all about. Rough outline of the paper and sort of where I'm going to go with it, just following along. They start out defining this storage service interface that kind of motivates the rest of the paper. Then they dive in and describe the algorithm for doing this chain replication. They talk a bit about comparisons to primary backup style replication, which is a bit more mainstream. They do some simulation experiments with some numbers that may or may not actually mean anything. Storage service interface. What does this really mean? Hopefully this is a somewhat familiar idea to people. A storage service is basically a big map from a key of some type to a value of some type. The operations that the service exposes, you can query it, you give the key, it gives you back, hey, here's the value right now. And then you can do an update to change the value that's stored. So specifically here, they're not constraining themselves to just a put. They can also represent more interesting things, like compare and set, where you said, okay, I'd like to change the value to 5 if the value is currently 7. And more complicated stuff like that, but always within the boundary of a single object, so no cross-object transactions. They describe kind of a basic state model for this system, and then the implementation kind of uses this to prove that their implementation using chain replication does actually implement this API. So basically the abstract state that this system wraps is for each key, a history of all of the updates that have ever been applied to that key. You probably are not actually going to store all of those updates. They say explicitly in the paper, but it makes the argument a little bit easier if you think about it. That way, usually you would just collapse that down to apply all of those updates and just keep the latest value for each object. So query then is defined as just a function over all of the history for that object. And then they also keep this idea of the pending set of requests for a particular key. So that's any request that has been received but not yet processed. So the state transitions in the system, if the client sends a request, great, you add it to the pending set. They say explicitly the system is allowed to ignore requests. This sounds a little bit weird, and you certainly don't want to do it a lot, but it makes the math work out, and they point out that this is equivalent to the client's message just never even gets to the server, so it's not a new failure mode for the client. Since you can never, at least with the networks we have today, you can never guarantee that that message is actually going to get there. So you can't tell the difference between the message never got there and the message got there, and the server just ignored it. And then, so finally, the third transition here is the client request is processed. So it just gets removed from the pending set, and then if it's an update, that request gets added to the history for that update. If it's not an update, if it's a query, then you just process the query and send the answer. So they talk a bit about some desirable properties that you might want from a storage service like this. So obviously high availability is one of the priorities. Doesn't do anyone any good if you have this big expensive storage system that isn't working right now. High throughput is important. You want to be able to send the system a lot of requests, both queries and updates, and have it be able to keep up with you. And then they say one of the things that they set out to do is to achieve strong consistency with this system. So somewhat controversial, more so now than it was then, but this can make it a bit easier to reason about writing applications on top of the system if you get strong consistency. So I guess they kind of break this down into two pieces that they think are important here. One is that the operations are linearizable. So essentially, given a set of things that happened, you can pretend that they were all executed one at a time by a single server, if they actually weren't. That protects you against some weird things, like if I send a compare and set from 0 to 1, and you send a compare and set from 0 to 2, exactly one of those should succeed, because either they happen this way and yours succeeded, or they happen this way and mine succeeded. We don't get into weird edge cases where both succeeded and the value is 1 and 2. And then they also say we want to guarantee read-write rights. So if I do a write, and then later I do a read, we don't just want those operations to be arbitrarily linearizable. We want my read to happen after my write happened. So let's dive in and talk about the protocol. So first, they make a couple of assumptions that are kind of important to get out of the way up front. So they assume servers are fail-stop. That means if anything goes wrong, the server just crashes and burns and stops doing anything else. This is a pretty common thing that people assume in distributed systems that actually get implemented, because the alternative is really hard. It's more or less reasonable. Obviously, it doesn't cover things like bugs or attackers or magnets or anything like that. If you're writing code for the space shuttle, please don't assume this. And also, they assume that failures can be detected. So if some server dies, that everybody else has some magical way to realize that that guy has died. That ends up being a little trickier than it sounds, because of the way networks work. It's really hard to tell if everyone else is dead or if I just lost my internet connection. People have ways to try to do it. It more or less works. So chain replication, how does it work? So we've got a bunch of servers. We want to replicate our data across them, because high availability is really hard if all of your data is on one server and someone kicks the power cord. So we want to keep all of these servers in sync so they all have the same data. So we organize them into a chain, and it's chain replication. The head is the first node in the chain, and then so on and so forth until the tail. Update requests go to the head. The head, runs that per single object transaction, decides what's going to happen, does this pass, does this fail, stores that locally, and then forwards on the result to the next guy in the chain. That guy can assume that this transaction has already been run. He just needs to apply that same update to his disk, forward it on, and so forth, until it reaches the tail. The tail writes it to disk, and then sends both a reply out to the original client saying, hey, great, this update succeeded, and then sends an ACK back up the chain so everybody else knows that it succeeded. Then all query requests get sent to the tail. The tail processes that query based on its local state, and it shoots the reply out directly. So hopefully it's, yeah.
Are they passing the message or the result of the message?
So inside of the chain, it can just be the result of the message.
The paper doesn't specify one way or the other? Or?
They don't really.
Here's a little bit when they talk about the modeling, right? So that if the head can, if it's a one-time expensive computation to get the value,
Yeah.
the head can absorb that and the rest of the guy.
There's no need for it to be the original request. For a lot of systems, the result is just going to be write this thing that the user asked me to write. So it's the same there. But if it was going to be some complicated transformation, you could do that once on the head and then just set effective it on down. So hopefully this makes it pretty reasonable to see how this gives us linearizability. The head gets all updates, so it can put them into some order and forward them on down the chain in that particular order. The tail can put in queries wherever it feels like, so you still get a single order there. And then because the tail is responsible for shooting out the replies for writes, if it shoots out a reply and then later you send a read to that tail, then you're guaranteed that you'll see your own.
And what's the purpose of acting back up the chain?
We'll get there. So kind of the formalism here, each node also has its local copy of the history of all updates it's seen. It also has the set of updates that it has seen and processed locally and then sent on to the next node in the chain, but hasn't yet got an act for. The system state that we talked about at the beginning, we define the pending set to just be all of the requests that any node in the chain has seen but haven't been processed by the tail yet. And history is just the history for the tail. We have a couple invariants that we want to maintain while the system is operating. So the first one is that the history of node I always has to be a superset of the history of node I plus 1. That's, in the happy case, that's pretty easy to see that that checks out because node I processes the thing and then sends it off to the next node, so it's always going to have strictly more updates that it's processed than the guy after it. Not strictly more or equal, sorry. And then second, we specifically want that the history on my node is exactly equal to the union of the history of the next node and the set of requests that I've sent him but haven't gotten an ACK for yet. So the happy case, mapping to the state transitions that we talked about earlier. So if the head or the tail receive a request, we add it to the pending set. When a query is processed by the tail, we answer the query, remove it from the pending set. When an update is processed by the tail, we remove it from the pending set and we add it to the tail's history, which is defined to be the overall history. So this checks out. If everything works as we anticipate, then great, we've implemented the system that we had said we're going to. But things are probably not going to work out. So we have to talk about what happens when things go wrong. So the paper describes a single master system. So you have someone outside of the cluster who is the master who decides when a particular node is dead and controls the configuration of what order posts are in the chain. You probably don't want this to literally be a single master. You probably want something like Zookeeper to give you a little bit better availability there. But it's worth noting that the master is not on a hot path here. It's just the master only needs to get involved when something goes wrong and you need to reconfigure the chain to get it working again. So the master detects when nodes have failed via this magical mechanism that we assume that we have. It reconfigures the chain to get things working again. And it's where clients discover who the head and the tail are, so they can route requests to the appropriate place. So what happens if the head of the chain fails? So here, my excellent little slide diagram. We start out, this is sort of the initial state of the system before anything goes wrong. We've got the head node that has processed 5 updates. The next node in the chain has processed 3 of those updates, and then the rest of the chain is there. So the head node dies. The master detects this and removes it from the chain. So now the new H+ node is now going to be the head of the chain. So this is actually really simple. The master just starts directing people to write to the next node in the chain. So we've lost some data here. Previously the head had processed requests 4 and 5, and we're lost now. But that's okay because we haven't sent any replies to the client yet. So that's just our transition 2, where we are allowed to ignore requests occasionally. So that's it for head failure. That one works out pretty easy. For the tail, if the tail fails. So again, we've got the nodes in our chain. The n-1th node has processed 1, 2, and 3. It's sent. It has sent 3 to the tail, but it doesn't have an ACK yet. The tail has processed 1 and 2. And then the tail dies. So again, the master detects that this node is dead, removes it from the chain. So the first thing it does, it tells the new end of the chain, hey, great, you've just been promoted, you're now the tail. So by definition, everything that the new tail is processed is good to go. So it takes everything in its sent set, and now it fires off a reply to that client saying, hey, great, congratulations, your update is successful. And it forwards X back up the chain to people in front of it. This is perfectly okay. This is just our transition 3 updates getting applied. The client doesn't care which tail applied the update, it just cares that a tail is applied the update. And the guarantee that T- has always seen more updates than T makes it safe to drop T without losing any updates. So once that's set, then the master just starts directing queries to the new tail. So now we're going to get to ACKs. Be excited. What happens if something fails in the middle of the chain? Again, same setup. Node S dies. So the master detects this, pulls it out. The master asks the node after it, hey, how many updates have you processed? It then tells that to the node before. So now the previous node forwards anything from its sent set that hasn't made it down to that next node there. You see here, we had already sent 4 down to that middle node, but it hasn't made it all the way to S+. So this is basically retrying that update propagation, skipping over the node in the middle that's dead. Then once it's forwarded out those sent items in order, then it just keeps on. As normal, with that is the next node of the chain.
So we're assuming that writes are idempotent. So if
They don't.
S+ had received 4 twice, so if that lost in the network and then showed up again after S disappeared, and then it gets 4 again from S-.
Yes.
Yeah,
So it is, you keep track of essentially how many updates you've processed. So that's in this step. The master asks S+ how many updates it's processed. and then tells that to S minus, so it can send all the updates that.
Right, and then should S had S sent 4 and then died.
Yep.
4 trickles in, 4 from S arrives at S plus. At the same time, then S minus could send 4 to S plus, right?
Yes. So they are.
We have to assume that they're idempotent then.
They're idempotent at this point. So when they hit the head, they're not necessarily idempotent, but the head assigns a unique ID to each one, and then so if you get 2 updates that have the same ID,
Right.
process one of them. I was wrong. We didn't actually get the apps here. Sorry. They're coming. I promise. So here we've killed the chain, right? So all of these, whenever anything has gone wrong, we've just killed that node and let it die. You can obviously only do that for so long before things are going to get real tricky. So we want to be able to extend the chain and add more nodes back in to keep our replication vector up as nodes fail and fall out. So we need to talk about how we're going to safely extend the chain. So we do that by adding a new node at the end. So we start with the new node, it's got an empty state. We tell the old tail, hey, just forward a snapshot of everything you have onto this new guy, and start tracking all of the updates that you're applying so that once you're done sending a snapshot, you can start sending those off in order. So once that snapshot is replicated to the new node, then we again have this update invariant holding. And then we start forwarding on everything in that send set. When that's small, then we'll do a quick switch over. So we'll tell the old tail, hey, you're not the tail anymore, stop responding. When you process an update, stop sending out a response to the client, just forward that on to T+. And then we tell T+, hey, whenever you process anything, send out a reply to the client. So that kind of handshake, make sure that we're not, that the tail isn't sending replies for things that are going to end up not actually being processed by the new tail. Once that's done, then we switch queries over to the new tail. And then that's, there we go. We've now extended the chain by 1. Are there any questions about that? Does that make sense? Do people feel like this is actually a safe thing to do?
In last 5.
Yeah.
So the new tail switchover will take place after blocking the replies from the old tail.
Sorry, what?
Will the replies from the T will be blocked and then new tail will be switched over?
Yeah, so first we block replies from T, and also T stops responding to queries. And then once everything is forwarded over, then, so there is a little outage here where T is not responding to queries and T plus is not responding to queries right now until T plus has applied everything that T sent a reply for.
There will also be a time when T is sending a snapshot, but could it happen that T might get a new value? And
Yeah,
that
definitely.
new value might.
So between these two slides,
Yeah.
we see T processed 4.
Yeah.
T sent out a reply for 4. That's fine. Transferring the snapshot in general is going to take a while, so we don't want to block things from happening while this is going on. So essentially T plus is not yet the tail. T is still the tail here. T plus is just catching up. And then, so we're building up a buffer in the sent queue while that's happening. And then once the snapshot is transferred over, then we burn down through that sent queue until that sent queue is small enough that the outage, while we finish transferring that sent queue to the new tail, is small. Cool. Charge on ahead.
I think you were asking, or maybe, I don't know, that technically T plus may have ingested some of the queue that he's going to get reset. Right? If he's just like reading raw the entire applied queue of T, that may already have 4 in it. And then he's going to go ahead and apply 4 again.
Yeah.
So they don't look redundant, but since they're idempotent,
Yeah, they don't explicitly talk about that.
if they're like in place updates, right?
They talk about it just as you atomically take a snapshot
Yeah,
of
right.
T and
Magic.
transfer it,
Yeah.
and then you transfer everything else. In practice, taking a snapshot of T might be a really bad idea.
Right.
And so you might want to ship the update and then just rely on the fact that, yeah, I might have some updates that were in that snapshot, but
That just looks like
you'll just
an
apply it
override.
again. Who cares?
Most is working kind of thing. If I see a update which is not larger version of what I reply, it's this will update.
Yeah, I think the thing is, T plus may have data or whatever for it, may actually have it file already, but not know that. He's copying T's raw brain. He may not, he's not, as he was hinting earlier, he may not have the entire history of the entire object. So. Like technically T plus might be able to enter it very early and not even know to know what things.
Yeah.
But once he applies for it, then he knows he can.
Cool. So the next section of the paper, they kind of do a comparison of this approach versus a more traditional primary backup. So just a quick, if you're not familiar with primary backup, it's essentially the same kind of thing. You're sending all updates through a single master to serialize them. But here, instead of forwarding updates serially down the chain, the primary basically does everything. The client sends a request to the primary applies that locally, then sends it out in parallel to all of the backups. The backups send ACKs saying, great, I got this. When the primary has what it considers to be enough ACKs from backups to ensure that this is durable, then it fires off an ACK to the client. So the kind of high-level analysis of the differences here is chain replication. You can think of it as a kind of primary backup, where the primary is split between the head and the tail. So the head is in charge of doing the work of applying the updates, if that's more complicated than just bits on disk, and in charge of ensuring that updates happen in some particular order. And then the tail is responsible for answering queries. So what this ends up leading to is you get better overall throughput compared to a primary backup system. The primary backup, your primary is essentially doing a lot of work, and all of your backups are doing just bits, disk, bits, disk. Whereas in chain replication, you can share some of that load, and also share network bandwidth in primary backup, unless you're doing some kind of multicast thing and pushing it onto your routing infrastructure. The primary is sending out many copies of each write, whereas in chain replication, each node is receiving one copy, sending one copy, so you get a little better evenness there. So chain replication obviously distributes updates serially, which means your overall latency between when you send a request and when you get a response is going to be worse. It's going to be the sum of the latencies of all of those hops. Whereas with primary backup, you're going to get the max latency of whoever the slowest backup is, essentially, is going to be your limiting factor. But you trade that for better throughput. So failure recovery. Neither of these systems are available in the cap sense. There's a partition. Both of these fall over, at least if you're on the side of a partition that can't form a majority. So for chain replication, both of these get high availability by saying that they're going to be able to very quickly reconfigure things so that it works at least on the majority side of the partition when somebody is. So they talk a bit about how they feel chain replication is able to recover from failures more quickly than a primary backup. So in chain replication, if the head fails, you can keep doing queries, because queries go to the tail. That continues without any problems. Updates are going to be down because clients are still forwarding updates to the master, or the head rather. So there's a 2-message time delay. You have to send a message to the new head to say, hey, congratulations, you're the new head. Accept writes, and then you need to send messages to the clients to say, hey, write to the new head. If a middle node in the chain fails, neither updates nor queries are immediately affected, but updates are going to be delayed. Basically, they'll come into the head of the chain, and they'll get as far as they can, and then they'll just stall there until the master can reconfigure things to skip over the failed node. And then those updates will be applied just a little bit later than you maybe hoped. If the tail fails, updates are still going on, delayed in the same way as for middle failure. Queries are down until, again, sort of the same thing as a head failure, until you tell the new tail, hey, congratulations, and then you tell the clients, hey, leave from the new guy. For primary backup, kind of the big problem here is that if the primary goes down, everything is down, and it takes a long time to reconfigure things because you don't know who the new primary is going to be. So essentially, your master in this scenario needs to talk to a bunch of the backups to say, hey, which of you are actually up to date and willing to serve as the new primary. Gather up all those responses, figure out who the new primary is, tell the new primary they're the new primary, and tell clients to talk to the new primary. If a backup fails, updates are down basically until you can tell the primary that guy's dead. Don't wait for acts from him. Queries, depending on your implementation a bit, can be down for some time. So for clean rows, where the primary knows that it doesn't have any pending updates out for this row, it can just answer immediately if all of the backups are dead. For dirty rows, where it's committed something, but it hasn't gotten enough acts yet, it basically has to wait until either it gets those acts from backups, so it knows that the write that it committed is actually committed, or else it has to wait for a message from the master to say, these guys aren't going to send you acts, it's okay, you just go along with that then. Another slide. Nope. So the basic summary here is the worst case for chain replication was just 2 message time waits for either updates or queries to become available again, whereas the worst case here is 5 delays while everything is down. And the best case here is there's no availability impact at all, whereas here, if any node goes down, you have some availability impact. So the next section, they built some simulations, not on actual real systems. I think they just made some.
The first bullet point.
Yep. So they assume they had infinite bandwidth. They assume always the latency for sending a message from one node to another is 1 millisecond. They assume it always takes 5 milliseconds for the query to for the tail to process a query. Maybe it's doing one read down to disk, but that's cached maybe some of the time. They assume update latency for processing that first update on the head is 50 milliseconds, and applying a pre-calculated update at one of the other nodes is 20 milliseconds. I have no real idea how they came up with these numbers. So take everything I say from this point on with a giant grain of salt. The simulations, they have 25 clients that they've simulated, each just sending a single threaded loop, send a request, as fast as you can. Send a request, wait for a reply, send a request, wait for a reply. So these graphs are a little tricky to see, but basically the x-axis here is the percent of the workload that's updates versus queries, and then y-axis is total throughput in terms of number of queries and updates you get processed per unit time. And then the 3 graphs are with 2 nodes, with 3 nodes, and with 10 nodes. So you can kind of see the two, this is their simulated primary backup, this is their simulated chain replication that does a little better. This is their weekly consistent version of both primary backup and chain replication, and apparently didn't matter enough to graph them separately. So you can see you pay a big price for getting consistency, at least when you're read heavy, because their numbers are skewed so far in making writes very expensive compared to reads. When you get out far enough, you just have that dominates and everything ends up approximately the same. But in here, hooray, chain replication does a little bit better than primary backup. So the next piece they talk about is, up to this point we've been talking about a single chain. Obviously that's going to hit a scaling limit pretty fast because you can only pump reads into this single tail node and writes into this single head node so fast before that machine just falls over. So very similar to pretty much every other storage system that I've ever seen. The solution to this is you run multiple chains, and then you use a distributed hash to map object keys to a particular chain. So the next set of simulations are all something like this. Servers can participate in multiple chains. Since those middle nodes are doing much less work than either the head or the tail, it makes sense for a single server to be the head for some chains and middle node for other chains to kind of more evenly distribute the load across their set of servers. So for these simulations, they did 5,000 chains, each chain with 3 servers in it. The same 25 client load randomly distributed across different chains. So this is their graph, and you can see, hooray, we get a curve as you add more servers. And then you get, again, because of the difference in how expensive reads are versus writes, if your workload is mostly reads, you scale much faster than if your workload is more writes. So a bit of simulation about the effect of failures. Same kind of setup as the previous example. We've got 24 servers, 5,000 chains mapped across those servers. One of the things they're testing here is the effect of adding nodes back into the chain and the work of doing shipping off that snapshot to the new node that is just joined. So for purposes of simulation, we've got 100 gigabytes of data per server, presumably split across the multiple chains stored on that server. They don't really talk about it. Here, finally, they say we're going to give up on infinite bandwidth, and we're going to say for recovery purposes, we've got a little over 6 megs per second between servers, and we're going to, again, who knows where they came up with that. And they assume it takes 10 minutes from a server crashes until we can get it back up again. So here's their graphs. Things are chugging along, and then so x-axis here is time in hours, throughput of updates and queries on the y-axis. So things are chugging along. At 30 minutes, one of the servers dies, or 2 of the servers die. So you can see there's usually a big drop in throughput as things grind to a halt until the master can detect and reconfigure. Then things pick back up and start running again. In the query case, there's where they come back to is lower than where they started out, because now your workload is less evenly distributed, because so you killed those servers, and then 10 minutes later you come back, and that server is going to join as the tail of every chain that it joins, so it's going to get a disproportionate amount of query traffic to it, basically. So overall throughput is a little bit lower. You would theoretically want to do some kind of rebalancing there. They don't really get into it. For updates, we see this pattern where it kind of drops initially and then spikes back up, probably as for all of the chains where you have a middle node or a tail node die, those updates still hit the head, and then once the chain gets reconfigured, the chain is going to process those updates as quickly as it can, and so you get that kind of bump back up.
Why is the post-failure update rate higher than the steady state?
So I think this is, there's some, I guess even at steady state, it's still a little bit higher.
But I mean, they kind of converge at the end of the 2 hours, but
I think that, is it possible that that's counting the total traffic?
so they're applying a steady update rate,
And then,
they just catch up.
Yeah. So I think
Yeah,
it's some of
They
that.
have some queued updates, but then the area under that curve is way bigger.
yeah, but it's going to include the state that they're replicating. If that's what they're counting.
So they also say that
So it'll drop back off.
one of the things they think is some of the chains, after those servers die and they're pulled out, some of those chains are now only of length 2. So they felt like they were getting much better throughput through those chains.
That makes
And then that tapers off when you add back in a new node and it finally catches up, and then your chain is now back to regular
It
space.
takes an hour and a half for the chain stall to send to their normal through rate.
Yeah, they didn't talk very much about
Yeah.
what, how their
This is
master
here.
reconfiguration is working. So to, I guess, kind of wrap up, they felt that chain replication was a correct implementation that supported the kinds of strong consistency they were shooting for. They felt like it got better throughput than primary backup, fanning updates out in parallel, but worse latencies. and they felt like it got better availability than primary backup, although not high availability, kind of what people usually mean when they say high availability. Some other papers on this kind of stuff so this was sort of the original paper that described this idea. Two other papers that I really like, but I'm not going to try to get into tonight. Object storage on crack describes a system basically where using those acts that are traveling back up, once you know that write has been committed by the tail, nodes in the middle, you can actually use nodes in the middle of the chain to take reads for that kind of data, as long as there isn't another update that has gone through in the meantime. So if your workload is heavy on reads, you can send reads to some of those middle nodes.
So in that case, does the master decide whether this node has processed that update and there is no subsequent updates that, you know?
No, so the node can decide locally. So basically, if that record appears and it's sent, then it needs to wait until it appears definitively, or if it's tracking multiple versions of the record, that's a old version. If it doesn't have anything in its sent set for that record, then it knows it's got the same thing as whatever the tail has, and so it can just answer.
I mean, to be able to receive the query requests on that particular value.
Yeah, so clients just send requests to nodes in the middle, and then the node decides, can I answer this right now, or do I have to wait until I hear whether this update was actually successful? And then chain reaction, causal plus consistent, blah, 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 something. Kind of goes the other direction and adds additional nodes after the tail, or equivalently has a node in the middle of the chain sending replies to clients. And then this is essentially an eventual consistency where you can send requests to those nodes, and you're guaranteed that your read will be something that was actually committed, but it might not be the latest thing that has been. So both the themes here are kind of, we want to be able to scale out reads for a single key, where sort of the distributed hash table thing works out fine if your workload is balanced pretty evenly across keys, but you don't have a single key that's really hot. Whereas this allows you to take advantage of some of the replication to scale out reads for a single hot key as well. That's all I've got. Questions, comments?
I'm confused by higher latencies producing greater throughput, given a client model where they're just writing, each subsequent request waits on the previous. Just the simple model says throughput's the inverse of mean latency, and vice versa.
Yeah, for multiple, if you have multiple clients.
Right. Well, if you have a fixed number of clients, they're basically presupposing there's extreme elasticity in the concurrency of the clients. If you're going to get more throughput out of the whole system with higher latency.
No, it's a shorter chain, right? So the latency goes down.
No, they said the latency goes up.
Throughput.
Higher latency,
Is that what they said?
higher latency and higher throughput.
They're doing updates serially across all the nodes, so the latency is going up.
Yeah.
Compared to prime.
Right, because you don't act the updating client until the end of the chain has
I guess assuming you have enough clients to saturate.
So they're assuming basically highly elastic client concurrency.
Yeah.
Okay. Because my clients are infinite. As long as they're written installed. The spread.
Yeah, can it apply to a request 2 times? So when the tail goes down, if the tail goes down,
Yep.
the node before the tail, how will it know that what tail had replied?
Yes, so you can definitely reply multiple times. to a particular update, that's probably okay.
So, yeah.
I mean, in the same, depending on how reliable your replies are, it's possible even with a single tail, it's going to send a reply and it's not going to hear and it'll send a reply.
Is there an example implementation of this somewhere?
I'm sure there is. I'm sure it's, I'm not sure. I've never seen one.
You've written one.
I've written one that you can't look at.
I know, yeah.
I'm sure there are some out there that you can look at. I don't know that they're anything that I would recommend that you actually use for real, even if you were conceptually bought into the idea.
Isn't that true with almost all of it? What? Why do you get
Conceptually bought into the idea.
Um,
I mean, if you had to build a system like that had all the properties again, would you start with chain state?
I would.
Assuming that you have PAXOS and things like that that you can reach out and talk to, right?
I would do it this way again for my particular workload. I'm not sure that I would consider this for every workload that I can imagine.
They've not done a comparison with PAXOS in their charts. I mean, like, they compare the primary
Yeah.
backup.
So the way that I've mostly ever seen PAXOS implemented is you don't run a full round of PAXOS for everything. You use PAXOS to elect a primary, and then you just do the second phase of PAXOS to do updates until that primary loses an election, and you elect a new primary, and then that primary just does the second round of PAXOS. So it's effectively primary backup at that point.
Is there any mention to the way, this looks like how GFS replicates edits across,
So they do talk about GFS
they
a
talk
lot.
about that? I think the difference is that GFS acts from the leader, not acting from the tail. So edits go all the way down the chain and back up again before it will act to the client. They do talk about this a lot?
They compare, the main thing that they talk about is the GFS doesn't give them the strong consistency that they are interested in. I haven't actually,
Okay.
yeah, I don't know enough about how GFS works to get this something called.
So, real quick, again, about choosing it. What is the general shape? I'm not trying to figure out exactly why you built it, but what's the general shape of the workload that makes chain replication more intelligent?
So,
Or is that to do with your?
no, I think that's reasonable. So I was actually not, my updates were always appends, essentially. So my data is a log. So this kind of, my updates are always, the next write into the log is this.
Yeah.
And I just needed to be able to blast a bunch of data in the front end and then have a log of all that.
And the guy sending the appending to the log was not sensitive to the latency.
Not on the order of the 3 message delays
Yeah.
within a region versus 1 message delay in a region. To be fair, this is very much, I implemented it this way and it worked out well, so I would do it that way again. I can't say that if I had implemented it using PAXOS to elect the master and do then the other way, that also would not have worked just as well.
So where do you implement this?
In a previous job.
So, there's a form of primary backup where the primary doesn't exist. Where there's some consensus on the guy generating workload can see all three replicas. And it's just sending it directly to them.
Yeah, so that's essentially the client is the
Primary.
serves as the primary,
Yeah,
at least for this.
Right, even if he doesn't have
instance
durable
of
state,
access.
he learns it all out of the replicas, right?
Yeah.
How, can you, stand up in like 2 seconds, compare that to chain replication? Like if that guy had all that, if he had exactly the same thing, would it make sense for him to submit to a head and then let those three replicate each other and then come back to him?
So as I understand it, the problem with I read the state of all of these nodes is for that to be meaningful, I have to say, hey node, I want to read your state and please don't change your state until you hear back from me. Or some timeout elapses.
Yeah, I guess it presupposes that that workload generator owns that key space.
Right.
Somebody else gave it to him. You're saying that would be the key to
That's from a just standing up here off the top of my head.
I appreciate that.
And then, so then you do have the same, if you're going to fan out that right to end nodes, you do have the same network bottleneck of, now I've got to send out multiple copies.
And
guess
if we actually,
potentially
if one guy dies, have to figure out what to do with it, know which state's dirty.
Yeah, you're essentially the primary.
Usually storing the state that was dirty in the other replicas. So it's simpler.
You would theoretically save a little bit on latency by, rather than you sending to the master and then the master fanning out and then back to you fan out.
So your experience with it, does this seem simpler?
This was not ridiculously terrible to implement.
Okay.
A lot of the complexity is in the master who reconfigures things. And I got that for free, so that helped.
Presumably a place like that.
So did you kind of, so you, towards the end you mentioned like two papers, right? The crack and the chain reaction. Did you actually implement those two also?
Yeah, we did something similar to chain reaction, where you have additional nodes after.
And the better, I'm assuming that better performance.
Yeah, you can do more reads because you can share reads across all of those nodes if you're willing to have eventual consistency on those reads.
So reading from all of the copies doesn't give you something like eventual consistency? Was that the weak thing in the graph?
Yeah, so weak in the graph was read from a random copy. And you may read something that is not actually going to be which is different than eventual consistency.
Right, because it could still you could be reading from the head and he dies.
You could read from the head and then the head dies. And no one has ever found out about that.
But if you read from all but the head.
If you read from the second one and then the head and the second one die. At the
Oh
same
yeah,
time.
maybe up to some number of failures.
Yeah. And then, wherever that point is where you feel like you've got it on enough copies that all of those guys aren't going to die, then you might as well have that be the tail node and
Call that chain reaction.
Call it chain reaction.
Yeah.
I'm going to sit down for
But that's still a useful, I guess this gets into the whole how strong do you need these people.
Yep.
Yeah.
That depends on,
99% of the time, you just don't.
alright, if you're willing to return garbage with the writes that are in flight, you can always read from it.
Writes that are in flight and might not actually end up being a little tricky. Eventual consistency, where it might not be the most
Right.
relevant, but it was something that was true at some point.
But if you remove things like compare and swap. And
So you can still do compare and swap. You do it via a transaction on the head, where you send a request to the head that says, hey head, I want you to read your local state, and if your local state is X, then set it to Y, rather than you do a read from the tail, and then somehow lock everything so it doesn't change.
Yeah, you'd have to drain all of it.
Yeah, so you get that from the head, given that the head is serializing all of the
But
updates.
this is presumably the one place where it's not high-throughput.
Yeah, once the head decides what's going to happen. So they even talk about you can do things like set the value of X to a random integer, where the head decides what that random integer is, and then propagates to everyone else, set the value of X to this specific integer.
And maybe temporarily then random integer until the attack happens, and then finally it's settled on one. The head
So
may keep dying,
if the head dies, then your request is just,
and you'll get a new random integer, but you never saw the old one.
if you retry the request, the new head will pick a new random integer, but no one ever told you that the first one succeeded, so.
Or that the head even got it.
So the paper talks about using a sequence, right? Basically an ID that you send with everything. So for that, did you encounter any issues when you implemented it with that, getting that unique ID stuff?
No, I mean the head just says, here is the 75th update that I'm processing, its ID is 75. Here is the 76th update that I'm processing, its ID is 76.
So you used basically an increasing sequence and record.
Yeah.
And it's always the head that generates the sequence.
Good.
So in the primary backup model, so if you allow reads from the backup, is that like similar to the eventual consistent model?
It's similar to the read uncommitted model. Since it's possible that a write will hit the primary and one of the backups, you will read from that backup, and then that backup and the primary will die. To get eventual consistency, you need to do some kind of quorum thing where you fan out reads to enough of the backups that tell for sure if the thing you read is actually going to be committed. Yep.
So you said that you've implemented this or something like it? Do you find their simulation to be accurate to what you see in your implementation, or
I didn't do
wildly different?
I didn't do comparisons, and certainly the actual numbers were wildly different, but I was doing it on wildly different hardware than they were presumably thinking about. So
But did it follow similar pattern?
I just wonder, if the graphs take a similar shape, right?
A lot of their graphs are, again, sort of this comparative of how does this perform with X nodes or Y nodes or Z nodes. And we didn't really do that. We just said, we need this replicated 3 ways for durability, so 3.
And then it's sufficient. So you're able to make it good enough.
Yeah.
Whatever. Is there any optimization to forward it onto the next guy while you're, there can't be anything like that, right? Where if you thought your update was going to be slow, to make it durable. I mean, you could aggregate acknowledgements, I guess. Because the guy can't tell how many downstream guys he got.
You can definitely aggregate acts. You can batch up writes as well if you want. You can, but I might be going off into deep end here. You don't need to write the data to disk necessarily, because if you die, you're going to join at the end of the chain, and you can just say, I've only got stuff that I had on disk. So if you lost stuff,
So you're
there,
optimizing your recovery.
that's fine. Yeah, you're optimizing writes at the cost that if you do die and get added to the end of the chain, you're going to have longer to catch up.
But then you're dependent on some sort of failure mode, right? Like if they all died instantly,
Yes.
they would lose those rights.
Yes.
Unless they had some magic way of.
Yeah, you're then relying on the fact that at least one of your nodes is going to be up and having stuff in memory at all times.
Yeah, when you bounce some failure, then I guess it cracks or something.
Although, to be fair, assuming that if you put it on disk, it's always going to stay on disk is not really safe either. So.
Does it have to be a chain? Or could it be like any directly acyclic graph with a single source and a single sink? Is there any shape that works better?
Mm-hmm.
No.
It could, definitely. I guess, I'm not sure, well, if it's acyclic. Yeah, I mean, you could have one head and multiple tails. And then, I guess, then you have to reason a little bit about what, if I have multiple tails, which of them is the authoritative one if I want to do it weak. And if you're picking one of them, then any chain that doesn't end on a tail, it's unclear what that's actually. I wouldn't rule it out. It's an interesting idea. If you can come up with something interesting that is useful for, I'd love to hear about it.
I wasn't able to come up with anything that was easy to reason about, easier than chain at least. But it seems like you're wasting a lot of servers for the sake of durability, to be honest. If you pick a high T,
Yeah.
reasonably, like in practice, T is less than 5 maybe?
Yeah, 3 is probably okay. 5 is a little better. Mainly you would go longer doing something like chain reaction where you only need 3 of them to say it's durable, but then you've got a couple of extras at the end for extra capacity.
And then the durability is an accident because it's fit in memory. The durability and chain reaction to the guys past the tail is just an accident. Like they don't actually need it to be durable, right?
Right, so you're then assuming that by the time it gets to the tail, you've got it on enough hosts that you're not going to lose all of those hosts.
Right. And they only happen to have it durable on their disk or something because memory is too expensive for them to hold the whole thing.
Yeah, you could keep it all in memory there. So if nodes die, they may eventually be promoted into the actual part of the chain.
And then rebuild.
So I don't know if you want to at that point say, great, now I'm really part of the chain, so I'll quickly try to flush everything to disk. We just put everything on disk because we might as well. Those guys, at that point, you're not worried about latency because you've already set the reply to the server, so, or to the client.
You said when you implemented the tricky part was the master.
Yeah.
This part was just
They glossed over it pretty hard.
So for like a hypothetical failure mode. If you had a failure inside of the chain, and for some reason your environment can't detect that failure, will you effectively fill up that pipe and like poison the rest of your system? Or how can you prevent that?
Yeah, I mean, you eventually need, so the send buffer on the guy who is immediately before the fail node will start to fill up at some point.
Yeah.
That needs to
It'll just be that one?
start backing up.
Will there be back pressure further up the chain?
Actually, yes, back pressure will start at the head because it won't be getting max back. So yeah, eventually the head needs to say, I've got too much buffer space, I'm just going to start dropping.
Okay, so you would have like load shed or whatever spill over.
And then you're just hoping that the master will be able to fix things and save you time.
Yeah, I mean, what if happens like when you find yourself in an unrecoverable state? You build a good enough master? Yes.
I mean, it's not unrecoverable, right?
Well,
you can keep dropping
Or
until
an
the master
unstable
is around.
state, rather, it's an unstable state that you're stuck in. How do you recover from that? Can you evict people from the chain? From the master?
Yeah, so that's exactly what the master does when it detects a failure.
Okay. So eventually you would reason there's a failure somewhere.
Yeah. So you need some way to detect failure. Usually that's via some kind of a heartbeat, where a node has to talk to the master every X many milliseconds until the master says, hey, I haven't heard from that guy in a while. I'm going to assume he's dead and tell me what else to do in their head.
How does this compare to Dynamo? So I read like the first half of the Dynamo paper, and they do something similar where they have a node of rings and replicate it from K plus N nodes.
Yeah, so definitely that,
Sounds similar.
the idea of kind of having multiple chains and then hashing to get which
Is effectively.
chain.
So which one came first? They sound exactly the same thing, right?
The idea of distributed hash tables came before
Okay, so
either of them.
So they're both.
And that's pretty much in any system like this. You're going to do something where you hash the key to say which set of servers should I store this on. And then whether you're actually storing it on those servers by sending to all of them or sending it to one and then replicate it all. It's somewhat of a fun thing. In terms of consistency, these are very different. In Dynamo, you say, I'm going to try to write it to you guys, and if I can't write it to you, I'm going to write it to someone else, and hope that he tells you eventually. Whereas this, you have to write it to a specific set of nodes and in order.
So what scenario did you have to actually implement this?
Basically big volume. So you've got a bunch of hosts generating a bunch of data, and if you want to know a log that you can then read through and do stuff with.
And the head could presumably decide the ordering too,
Yeah. So theoretically, the head could say, "Oh, thank you for this write, but actually, I'm going to wait until I do 7 other things before I apply it." Cool. Well, hopefully that was interesting. If it wasn't and you'd rather hear about something else next time, you should tell someone about it.
What's next month?
We don't
I don't
know.
think we have a topic right now, but if anyone has anything they'd like to talk about or hear about, please share your thoughts either here or on the Meetup forum.
It's really not that bad. This is my first time presenting anything. And I don't think it was super terrible. No one threw any tomatoes at me.
I thought it was pretty good.
Yeah, it was very good.
So how many many of you are going to go and apply this now? How many of you think you will apply it in the next 3 years?
I'm like on the fence, actually. That's why I'm here today.
Yeah.
I mean, if it's like a 10-year-old paper and there's still not a lot of implementations out there, it's probably not a good sign.
Yep.
Well, that you know.
Well,
it's part
so,
of
I mean, that's not necessarily a reflection on the quality of the data.
Yes.
Right. My general.
Last month's problem was like a problem posed 30 years ago that was solved 20 or 18 years ago and explained 10 years ago.
Yeah, PAXOS is like that too, right?
Yeah. One day we will actually figure out why PAXOS works.
He'll explain it.
Yeah.
Cool.
That was really compelling. Thanks so much.
For sure.
I'll get back to it. It's just another button.